Welcome to my Commodore 64 Games memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Mega Apocalpyse, published in 1987 by Martech, coded by Simon Nicol, the title screen by Bob Stevenson, and the musician is of course Rob Hubbard. And I'm going to be using the tape version of this game, which has a lovely little cyberload, and it's got some surprises in store, especially with bitmap display mode. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are all always very much appreciated. First thing we need to do is that we need to study the tape turbo loader. And this is using a cyberload. I can see the cyberload now loading Mega Apocalpyse message appearing there in the tape header, which is visible as in the graphics map view, in the text screen debug view, using ICU C64, which is what I usually use when I'm trying to reverse engineer these titles. We have this rather useful ranged breakpoint, and we can see here that the turbo load code starts doing some stuff. It looks like it's clearing the screen and initializing the color RAM, and then initializing the cyberload display, and then at the end it uses this branch on not equal, so we'll go there, and there we go. The graphics map text screen debug shows that the cyberload message is going to appear even before it appears in the main Vice C64 rendered output screen. Of course, that's because the output screen for the C64 is synchronized to a frame, whereas the debug view is not. The code continues on in the extended 0 page area. What we're really interested in is that we really want to trap the code execution just before it starts running the game. So this kind of code here, it looks a little bit like gibberish, doesn't it? It doesn't look like it's got really valid opcodes. I mean, there's lots of noops and long noops within, absolute address, X, for example. And that's because this code is kind of obfuscated. I've seen this kind of code before. Eventually, there's probably going to be an interrupt which comes along, which actually interrupts this obfuscated code execution, and then we'll start actually running the real turbo load code. But we're really just interested in trapping out just before the game code starts. So let's skip ahead to that. For those not familiar with cyberload, this is what the cyberload looks like when the little animation is running, and here we are, we're in a nice little horizontally scrolling message there, which seems to be updating at 4 pixels per frame. Actually quite a fast scrolling message. The turbo load code is now running code all the way up at C400 approximately, which is quite high up in memory, and that's because the rest of the game code wants to load quite low down in memory. We can see that there's some code loading or data loading there at the beginning, or roughly, what is it, 1/3 of the way through the memory map. There in the ICU C64 memory map viewer, we can see that yellow bar, thin line progressing quite steadily as more and more data is loaded. We get to this rather lovely tape loading screen, Mega Apocalpyse. There's really quite nice shading in this. It really looks quite lovely. I can see there in the debug text screen view there, actually I can see that there's some remnants of what looks like a disk directory with megapic named, and also a file 8.500 to E000 or -E000. That's probably because this was mastered from some files on disk and then mastered using some kind of tape mastering system. So now we're running this code up at the turbo loader that has just displayed the scrolling message and is now displaying the bitmap title screen. We want to try and trap out the jump just before it starts running the game code. Since we know that we're running turbo load code all the way up at C400, C500, we'll put a ranged breakpoint for the beginning of memory, and then we'll put another ranged breakpoint at the end of memory. Oh, look at that. Well, there's a little interrupt or something else which happens, and it runs it's not an interrupt, it's going to be a subroutine up at CFFF, right at the end of the C000 memory range, just before the VIC chip at D000, so we'll just ignore that. We'll widen slightly the ranged breakpoint and we'll let the load continue, and then we'll see what code is going to execute next. I'm just going to zoom in to that what looks like a disk directory layout, right? So there we go, 221 blocks of file 8.0500-E000, and then the file name Mega Apocalpyse. That was up at the beginning of memory in screen memory, roughly 400 in hex. The default screen memory that the Commodore 64 uses when it first powers on. Coming towards the there we go. The ranged breakpoint has hit, and it's the ranged breakpoint all the way down in 0 page. Look, there's quite some code there at 9.7 in 0 page. It looks like it's continuing to do some turbo loading, but you can see there that the Commodore 64 screen has turned off. This is quite a common methodology where there's this last little bit of turbo load code which loads the last gasp bit of data, and that's going to be probably under the I/O or right at the end of memory, for example, and then this leaves the remaining memory, the main part of the memory on the Commodore 64, available for game code to load into, because generally speaking, the game is going to reinitialize all of these 0 page locations, so it's pretty safe to have some turbo load code just sitting away there right down at the beginning of memory until it does an RTS. Now if we hop out from this RTS, we'll see that we get to, oh look at that, so the return from subroutine address is at 480 in hex, which corresponds to that code which has been loaded into the default screen. And it's code which is sitting just after the turbo load code that was in the tape header, and it's just after that Mega Apocalpyse now loading message ... message. So this code, if we go to the PC again, this code stops the interrupts, it resets the processor port to the default values, it looks like it switches off all of the interrupts, acknowledges interrupts, initializes 0 page and extended 0 page, so from 0 all the way up to 3FF in hex. Then it looks like it calls some kernel initialization, then does a jump at 5822. This really does look like a nice tidy routine to tidy the C64 state just before executing the game code. So what we'll do is that we'll save out the entirety of RAM, noting to a file on the hard drive, on my PC's hard drive, from the emulator using the emulator's built-in monitor, which is really, really useful. And we'll save out the whole memory from 200 in hex to FFFF, which is at the end of memory. And we'll save out all of that, and then we'll see if we can compress it using my compression tool, which has a very optimal LZ-based compression. There are several options, but we'll use the maximum ultimate compression. And we'll turn on the flashy border as well. And we'll have the input file, there we go, and then we'll just have an output file, which is going to be the compressed output, so ctemp ma.prg, and we'll use the start address, and it's managed to squeeze the whole game down into B1, B9 bytes long, which, considering it was FDFA bytes long, is quite a good compression ratio. And there we go, we have a single file compressed, basically, in inverted commas, hacked and packed version of the game. Well, that wasn't too bad, was it? It was quite easy. Modern tools like Vice and ICU's C64 and Vice's internal monitor make this really, really, really easy. With the game loaded, we can see that there's a ton of data, not much graphics data, especially early on in memory. We've got a whole bunch of sprites there in the last VIC bank, but the last half of the last VIC bank is the Mega Apocalpyse title screen. Let's just double check. Yeah, the Mega Apocalpyse title screen is still there. Let's fill that memory with empty space, and let's save that file again, but we'll save it as a second file using the previous command. We'll save it as MA2. And then let's compress that and then compare the output size, and it should be a lot smaller because it's not compressing the loading screen. And there we go, from B1, B9 to A156 now. So that's even more memory saved. It's actually quite a small file, isn't it, for the whole game? I probably don't need to restore the memory from 200 to 3FF, but hey, we'll do it anyway. It doesn't really affect the compression ratio that much. And we have this rather lovely, even smaller now, single file version of the game, which might be useful later on when we're trying to reverse engineer what's going on in the game.
Get ready.
So back to ICU's C64, and we can immediately see there the graphics map in the bottom right hand corner of the screen there. Look, the graphics map is showing that actually the game is rendering into a bitmap screen. And the stars, particles, or whatever they are all rendered into the bitmap. Well, isn't that fantastic? It's a high-resolution bitmap. Well, there we go. It's even more unusual, isn't it? So we can see where the sprites are by comparing the output from the Commodore 64 to the output that we see in the debug graphics map there. And we can see that the planetoids and the player's spaceship are sprites, but the bullets are actually rendered into the bitmap. All of this, all of the title screen, all of the high score table entry is also in the bitmap mode, which is even more fantastic. The Apocalypse logo, which is scrolling up there, is actually sprites, like it was in Crazy Comet, right? The original version. So let's see if we can understand a little bit more about the Starfield routine. So if we look in the memory debug view there, we can actually see quite a lot of green in the second half of the memory bank, and green indicates memory reads. Let's zoom in a little bit so we can see what that looks like. The memory writes, the yellow stuff down at the bottom, at the end of the memory map, is writing into the bitmap data, obviously, because yellow is memory write. We've also got a ton of memory writes going on, and some memory reads. There's green there going on in the beginning of 0 page or extended 0 page, but this great big field of green in the just after the halfway mark of the memory view there indicates that there is, it looks like, okay, so when the stars are moving towards the player, the reads go from left to right, and we can see the trail of the green pixels with the fading out of the colour indicating older reads, and it fades out and the reads get older and older. But when Starfield rotates, the reads seem to be more random, more sparkly, if you like, in that green area. Now there is a large green area as well up in the top of memory, but that large green area up in the top of memory, I think it looks like samples, because the reads are going all the way through memory as in an orderly fashion from top to bottom. Whereas in the title screen, attract mode, there are no samples being played, it's just the SID chip playing its chip music. And yet this field of green memory read accesses going on here in the middle of memory still happens in the attract mode, and of course the attract mode is displaying stars. So I'm pretty sure that we can say that this large area of green here is going to be a lookup table. Right, so let's see if we can get some addresses there. That's what, 8E52 for example. I'm zooming in here into the bytes in the view to find out the rough start and end memory addresses. Okay. Now the way that we can understand this code is by, one, trying to trace through the code, but two, we can just play around with filling bits of memory. We know that it is not code being executed, we know that it's just memory reads going on. Let's save a snapshot first of all before we start really killing the memory, of course. So once we start filling chunks of memory, then we can see how the code reacts to those chunks of memory being filled. And look, by filling that range of memory, it's basically removed the stars from, what is it, 3/4 of the screen update and just leaving the last almost quarter with a few flickery stars here and there, particles, whatever they are, stars, right? Active. So it looks like, ooh, and I think I've got some extra memory addresses at the beginning of memory being updated too. That's interesting. Okay, so this looks like it might be a great big lookup table. Probably a great big lookup table based on zoom value and maybe rotation or something like that. Because the last quarter of the screen, because I did not clear the whole lookup table, the last quarter of the screen is still there. So it looks like it's a huge, great big lookup table. I think if I change those values, look, the star position for the other quarters, for the other 3/4, changes the position of the star. So yeah, it looks like it's a kind of like a very fast position update lookup table, or maybe a couple of lookup tables in that range of memory, but basically, yeah. So let's see if we can find what loads from there, and using that little breakpoint there to look at the load address, or what loads from 8E00, we can see that we're in the middle of what looks like a plot routine. So the load indirected with open bracket $07 close bracket comma Y there at BF16 is an indirected load into that large green lookup table that we were just prodding and poking around with just now. And it looks like there's a load accumulator with 280, X there. So X seems to be a common register. Y seems to be a common index register into the lookup table. Okay, and Y also seems to be used as a general purpose index register. But X register doesn't seem to be updated apart from maybe at the end of this routine. If we keep on scrolling down, there we go, DEX BMI to BFB8. So it looks like X is basically being used as a star or particle index, and Y is, the Y register is being updated as a general purpose index register. That's fine. It looks like the table that we noticed at the beginning of the graphics map, sorry, not the graphics map, the memory debug view, was showing quite a lot of reads and writes, those large yellow bars there indicating memory writes. Those seem to be star position update information, or star position information, or maybe star zoom and rotation information. It wouldn't make much sense to have the star X, Y, and Z position in memory, because you know that you're going to be dealing with a zooming towards the player star field and a rotating star field. So all you need really is a rotation value around the center, and then the zoom level for each individual star. So that's probably what that is that it's probably using a rotation around the center and then a zoom level, and then looking that up into this huge, great big green lookup table, and then storing into the bitmap for each star. So that's really quite cool. That's a very optimal way of doing this kind of star field update. Now, if we count the number of stars here, I think there are around about, it looks like there's 64 stars that are approximately visible. Not all of them are going to be on screen, but I would have hoped that with the lookup table most of them would be. So yeah, that's 72 stars in decimal there. So yeah, during the game it looks like there are fewer stars being executed than when during the title screen track mode. We'll double check that in a second. So here we are at the beginning of that routine, and the line highlighted in red is loading X with BDEC. BDEC currently contains 48. 48, which is 64 plus 8, which is 72. So that's 72 stars that are active during the game. There are more sprites running around, right? And there's going to be extra stuff running, like the sound samples. So I would have thought the game would run slightly fewer stars. We can see here that every time I continue the breakpoint, this is 1 frame advanced during the star field update, which is quite cool. This routine here definitely looks like it's loading star positional information, rotation and zoom probably, and then looking it up in that lookup table. Let's see if we can find out where... I'm not very good at this game. I keep on dying very, very quickly. So playing this, it doesn't look like there's any updates, self-modifying code updates into the beginning of what looks like a star field plot routine. So we can delete that range breakpoint. And we can look to see what stores into BDEC. BDEC is the number of stars, I think, being active in the game. So there we go. During the title screen, so going back from the game to the title screen, it looks like it was storing 7F into BDEC, which is 127 in decimal. So yeah, there are definitely more stars active during the title screen than there are during the game. That's interesting. So if we start the game, we can see, well, first of all, that's restoring 7F into BDEC. That went into the title screen score, high score table display. Right, so that's definitely storing 7F into the title screen loop. There's the planetoids title screen and track display. That's fine. And then again, once it goes back to the other part of the title screen, there we are. It's reinitialized that back to 127 stars. That's also cool. Looking at the code there for the star field routine, let's just fill one of the tables. One of the values for one of those tables. Let's fill all of those values with 7F. And look, the previous stars are left on the screen. That's really interesting to note. So if I do that, then you can see the previous stars are left and then new stars appear. And I can keep on doing that and then the previous stars are left on the screen. So it's not removing the old stars when the stars positional information, whatever it is reinitialized back to unexpected values, which is quite an interesting way of debugging this. It means that we can see that actually the game is going to be probably removing and then plotting stars as one great big continuous long process. And then if the positions change from one frame to the other, then just the previous graphics data, whatever it was, plotted stars, the text on the screen, etc., is just going to be there. That's interesting. It's quite an optimal way of doing it. Let's see if we can dig into the star rendering a little bit more. So let's see if we can find out where the bitmap update is. And that was very quick, wasn't it? And that's because there are lots and lots of stars being drawn in the title screen. Well, okay, we have a load, absolute address X, E or FF, and with E0B8 store, and then we have a load ATA and branch equal to store. Okay, so this looks like it's basically looks like the and there is to remove the previous star, and then the next piece of code there at BF61 is to draw the star in the new position. The remove star and draw star are just basically updating those memory addresses and as absolute memory addresses, and that's fine. It's just self-modified code that has self-modified those addresses. We can see there that the self-modified code is a BF47, BF4A, for example, that's storing into BF5C, BF5F, which is updating those absolute memory addresses. So yeah, the game pretty much very quickly removes the old star and then plots the new star in its new position, all within a few opcodes. That vastly reduces the amount of time that you see between the updates of old star and new star, which means that the game is not going to have too much flickering. All you're doing is updating 1 byte within the bitmap, maybe 2 bytes in the bitmap if the star is really large, and that's not going to have much flicker at all, because the raster beam is constantly moving down the screen at 60 frames a second, or 50 frames a second if you're in PAL. I'm running the PAL version, it should be 50 frames a second, right? The raster beam is constantly moving down at 50 frames a second. It's not going to catch a star being redrawn very often. In fact, it's going to happen very seldomly indeed. So we can see every time this code runs at BF56, it is removing and then drawing a new star. And then that store there, because you're doing an EOR with FF and then an AND, it's basically looks like it's ANDing out the old star's data and then drawing in the new star. So we should be able to see individual stars being updated every time I progress the breakpoint. Let's change the number of stars to be something like 7. BDEC was the number of stars for the memory address there. We have a small number of stars now visible on the title screen attract mode for the high score table. If I now use the breakpoint to break on the star draw routine loop, we can see that the individual stars, well, the 7 or 8 stars now are just very quickly rotating around in that bitmap view. So it's easier to track. We're not seeing tons of stars now, so it's easier to see individual stars. Let's put the breakpoint now into the actual draw routine itself, and then let's single step now. And now we can see the individual stars being removed and then drawn in their new positions. And that because there are so few stars, it's easier to see the stars now when I advance the breakpoint. So we've got these few stars here. Just watch when I progress the breakpoint. Watch the stars in the debug graphics map view there. I advance the breakpoint and then you can see the individual stars just moving along, zooming towards the player or rotating or whatever it is that they do, just on an individual basis. So this is the core of the star field plotting routine. It just basically removes the old star, draws the new star into the bitmap. I have a crazy idea. Let's completely clear the bitmap. E000 to FFF7, there we go. I've cleared the entire bitmap, as you can see in the debug graphics map. Now as I progress the breakpoint, you can see the individual stars are being drawn. If I single step through this routine, you'll be able to see all of the calculation that this routine does, and then we'll see the individual stars in a moment. As it gets towards this breakpoint, here we go, it's still doing an awful lot of calculation. Those logical shift rights could be optimized into a table, but hey ho, never mind. It would be quicker to optimize it into a table, I would have thought. Never mind. But yes, it removes the old position, updates the position, and then it uses the updated position and then based on the table, and then it replots the star in its new position. So here we go, stepping the instructions, watch the star on the right, it disappears and it reappears in its new position. So the disappearing and then reappearing star is a matter of several, like 3 or 4 instructions, maybe 5 instructions. Not much time at all, a very small amount of time. Let's just show that one more time. There we go, the star's gone, and then stepping through a few instructions, and then the star reappears in its new position. So let's go back to the title screen and then clear the bitmap view again, and then we'll exit out, and there we go. We can see now the star field in all its glory without any text in front of it. Let's get rid of the text again. Wow, there we go. Doesn't the star field look fantastic? It's a really great effect. The game has done a really, really good job. The program has done a really, really good job, obviously, of optimizing the star field draw into the bitmap screen, into a single buffered bitmap screen, no less. For the star field to have this rotation and zoomy effect, it just basically uses this huge, great big lookup table, which is probably rotation and zoom level. And that would correspond to how the reads look like they're randomizing or reading from random memory locations when the stars rotate around, because the rotation would tend to drastically change the position in the lookup table that's being used, whereas zooming into the stars is probably sequentially stored into this lookup table. So yeah, that's how this routine seems to explain the memory patterns that we can see in the debug view. Now on to what we look like as the sound samples. This load breakpoint at 2665 was in the middle of a green area of memory at the beginning of the game's memory, and it seems to be trapping out on this code here at 21 in hex in 0 page. Immediately I can see at 2C, and well, I can see some NMI timer based DD0D as well, but D418 is basically an update into the SID volume register. Now, we can see there the code starts executing at 2.1 in hex. If we have a look there, we can see that F8, F9, FA, FB is going to be the NMI, the non-maskable interrupt vector, all the way up at the end of memory. There we are, FFFA is the NMI vector. That's just to remind me. This is a very useful ROM listing from one of the old Commodore 64 technical websites. So yes, FFFA is the NMI vector. So the non-maskable interrupt vector, the NMI interrupts can happen, for example, on timers, or when you press the restore key, or on the user port as well. But NMI vector at 221 is for the sample playback. I'm pretty sure of that, because I already saw at least one D418 register being updated there. It's loading from an absolute memory address. Branch equal to 4.1. That's going to a different routine. It looks like it's changing the vector for the eventual code, which is executed as an NMI based routine. Looks like that's turned off the okay, so when samples are played, almost certainly this routine is started by restarting the NMI timer or enabling the NMI timer. It looks like it's doing a store accumulated with 2D418 there. I can see another D418 update there at location 55 in memory as well. So it looks like, because I can see some shifts, I can see those 4 LSRA instructions at 28, 29, 2A and 2B in hex there as well. So what this looks like to me is, looks like the sample data is laid out as 4 bits in the lower nibble and then 4 bits in the higher nibble per byte. Don't forget that the SID volume register is 4 bits, values 0 to 15 in decimal or 0 to F in hex, and that's the volume register. And the volume register, when you store values into it that change rapidly, it causes clicks on the output speaker, and then those clicks are different volume levels, and of course it plays samples on the SID. So the SID chip wasn't initially designed, I don't think, to play samples in that way, but changing the volume register works really well for playing samples. So yeah, the sample data is laid out low and high nibble, and it looks like this NMI routine is optimized in such a way that it plays the low nibbles and then the high nibbles, and then it looks like once it gets to 0 in the sample data, it looks like it completes the sample. That looks like it's an end marker for basically turning off or acknowledging, turning off, I think, the NMI timer. So it looks like the code somewhere else in the game will turn on the NMI based timer routine to start pulling in sample data from the memory, and it plays through until it reaches the end sample marker and then completes that. So that's a really good way of playing samples. Storing the code for the sample player in 0 page means that you don't need to use indirect addressing, because you can just increment the 0 page registers themselves. The first page in zero page I call extended registers, and that's because it's almost as fast to update those as it is the index registers X and Y. So using this method, you can very quickly update the absolute address value just by incrementing the 2 bytes in zero page. You increment the low byte, branch not equal, increment the high byte. And that's what this code is doing, is that it's doing an increment, branch not equal, and then it's going to be looping through and then doing the high address increment as well at some stage. Right, so this routine here, it seems to do pretty simple sample update or sample play and update in an optimized way. Basically, the low byte, high byte packing for the sample data for the low and high nibbles in each byte is a way of optimizing the memory for the samples, because you can store 2 samples in 1 byte. You've basically doubled the amount of memory. There are other sample compression schemes on the Commodore 64 where you can have a run length encoded sample stream, where the low byte is the sample volume data for the SID, and then the upper nibble, is going to be the run length encoding. You can do that too, but this game doesn't use run length encoded samples. It's just using a strict low byte, high byte, and then playing the samples back at a steady timer-based speed, and that's a really efficient way of doing it. I think I've covered everything that I wanted to cover in this game. The single buffered bitmap screen, the star field update using the large lookup table, and also the sample sound effects. So this game was a real blast from the past. I really enjoyed playing it when I was much younger than I am today. It's dredged up a lot of really good memories of late night game playing sessions with my friends on my Commodore 64, and I hope you enjoyed watching this kind of deep technical dive video into old Commodore 64 retro games as much as I have done in making this video. So if you really like what I do, then please do consider liking or subscribing to this channel, and a super thanks is always very much appreciated, and you get your name in a little scrolly message roughly at the beginning of the video. Take care, have a great day or evening or night, and thank you for watching. Goodbye.